There we go. Toda raba lemeyorganim. Many thanks to the organizers. It's most certainly a pleasure to be here and to be part of the celebration of an effect that has become the namesake of many, many papers and talks, including, of course, the present one. I will start with just a brief historical introduction, because I'm sure that in this expert audience, an introduction is only needed by way of a warm-up, if at all. Thus, in 1959, the effect was discovered. Then in 1977, Leinas and Mirheim, and in 1981, Goldin and collaborators, using a different argument, proved that in two dimensions, particles can possess fractional statistics, that is, intermediate between bosonic and fermionic. The next important step was taken in 1982 by Wilczek, who connected the two concepts, showing that the former, in fact, implies the latter. The argument goes like this. If there is a composite particle consisting of a charge E and a flux phi, then an interchange of two such particles can only yield a phase, because it doesn't change the quantum mechanical state. The phase we can denote by e to the I pi alpha without any loss of generality. Now, a double interchange yields twice the phase, but on the other hand, it is topologically equivalent to pulling one particle all the way around the other one in a circle. Enter the Aharonov-Bohm effect. This phase is, of course, nothing but the product of charge and flux. And therefore, we have the expression for alpha, which is this same product divided by 2 pi. And the particles do acquire fractional statistics. It is they turn into what Wilczek called anyons. Having said this, the next step is so simple that I am not even sure who said the word first. I have listed here the names that I'm aware of, and I do have to apologize if I have done someone injustice by not mentioning them. Be that as it may, the step is to consider distinguishable particles with different charges and fluxes. Now, of course, a single interchange is not interesting because it changes the quantum state, but a double interchange, that is pulling one particle around the other one, is still interesting because, again, it can only yield a phase of alpha AB, where A and B now number the particle species. The only slightly non-trivial question here is what is the expression for alpha AB? Which charge times which flux? And it turns out that the center of mass motion in this system only decouples if the charges and fluxes are proportional to each other. And then the expression for alpha AB is simply one charge times the other flux, or vice versa. It's symmetric. All this has been simple, but if we pause here for a minute and think of the implication, it's really non-trivial. We have just proved that in two dimensions there is a notion of statistics of distinguishable particles, something that's really unthinkable in conventional quantum mechanics. Having said this, we now have to proceed to formulate a quantum mechanical problem, which involves a many-body, multi-species wave function. And if we denote a little bit loosely speaking by P, the anti-clockwise interchange of two particles, then we can still impose this condition here for identical particles. But for distinguishable particles, as we just discussed, only a double interchange makes sense. So there is the wave function with these conditions. Note that while alpha AA equals 0 corresponds to bosons, alpha equals 1 to fermions, in this case, for the cross-species statistics parameter, an integer is as good as 0 because of periodicity. So, for example, alpha equals 1 means no statistical coupling at all. How does the wave function that satisfies these interchange conditions look? The expression is here, and you will, of course, recognize the familiar Jastrow-Laughlin type factor, except alpha is fractional here, not integer. You see that when we interchange particles j and k, the complex difference of their complex coordinates picks up a phase of e to the I pi, hence this picks up the phase of e to the I pi alpha. So we have a factor like this for species 1, a factor like this for species 2, and a cross-species factor involving the cross-species statistical parameter. And in fact, the only indication that we have two species here is that the symmetric part of the wave function need only be symmetric with respect to interchange within this species and within this species, but not with respect to z interchange with zeta. Well, this wave function is non-trivial because the coordinates here are really entangled. With a fractional alpha, you cannot expand this as a binomial in terms of single particle wave functions. And as a result, it's only the two-body problem, as originally showed by Wilczek, that is exactly solvable. But even the three-body problem can only be solved numerically, although there is a subset of states that can actually be found exactly. This holds true for usual single-species anyons, and this holds true for multi-species anyons alike. Now, if we know at least approximately how to solve an n-body problem, one useful thing that we can do is evaluate the virial coefficients of up to the nth order. This is, of course, standard textbook statistical mechanics. The virial expansion is an expansion of pressure in terms of density. If we have two species, and for more than two, nothing is principally new, so I will just consider two. For two species, we have two densities. And I have extracted the dimensional factor in such a way that my virial coefficients are dimensionless. For completeness sake, I will mention that, of course, this also includes single species virial coefficients, where K2 is 0, so that rho 2 is not at play. As I said, the two-body problem is solvable, so the single species second virial coefficient is known exactly. This is a well-known formula. Note that it increases with alpha. Indeed, the pressure of a Fermi gas is bigger than the pressure of a Bose gas. The third and fourth virial coefficients have been calculated approximately, numerically. And here we would like to turn our attention to the mixed virial coefficients, which involve the cross-species statistics parameter. The expression for A11, the coefficient of the second order, is quite trivial. Again, it can be obtained from solving the exactly solvable two-body problem. Note again that alpha 1, 2 equals 0 is the same as alpha 1, 2 equals 1. In both cases, the mixed virial coefficient vanishes, which really means that there is no statistical coupling between the two species. The next interesting coefficient is the mixed one of third order, which depends on the intraspecies and interspecies cross-species statistics parameters. We have calculated it numerically, and I present it here as a plot as a function of its two arguments. There is an analytic conjecture concerning what this function might look like that goes way beyond the scope of the present talk. And I will just mention again that for alpha 1, 2 equals 0 or 1 alike, this mixed coefficient vanishes. Again, there is no statistical interaction between the species. Having said that, there is an actual n-anion problem which is exactly and completely solvable. Specifically, the spectrum of n-anions on the lowest Landau level of a magnetic field can be found exactly. Well, of course, for the purists among us, this is not a complete solution of a problem. This is only a subset of the states. But practically speaking, it is interesting because if the magnetic field is strong, then it is indeed only the lowest Landau level that contributes to the partition function. So this subset of the spectrum is actually interesting. Well, this subset has been found for single-species anyons, and it can also be found for multi-species anyons. As it turns out, the statistical interaction between the particles of the same or different species is, a little bit loosely speaking, a pairwise effect. Because from this expression here, you can see that the effect, the change in the energy that statistics brings about is the number of pairs of particle of species 1 times the corresponding statistical parameter, plus the same for species 2, plus the number of cross-species pairs times the cross-species statistics parameter. Well, since we know the exact solution for any n here, we don't even need to resort to the virial expansion because we can write down the exact equation of state. It is given by this formula expressed in terms of the Landau level density. And some comments concerning this equation are that first, if all the alphas are 0, if there is no statistical interaction at all, and if further rho is very small, then you expand the logarithm and it becomes the ideal gas equation of state. When you sort of switch off statistics, when alpha begins to grow, the pressure grows, which is again kind of natural. There is a statistical repulsion as compared to bosons, so the pressure grows. It is actually a little more subtle than that. There are some subtleties concerning this equation, but there is no way I can discuss them within the time allotted. I will conclude my talk then by briefly illustrating two results that have to do with a particular case of multi-species anyons, namely the problems involving anyons and static Aharonov-Bohm magnetic fluxes. The fluxes are, of course, just your multi-species anyons with infinite mass, which is why they are static. Sometimes we call these magnetic impurities. The two-body problem is again trivial, and of the three-body problems, there are two. One particle plus two fluxes, or two particles plus one flux. For one particle and two fluxes, we have studied the dependence of the energy, eigenstate energies on the values of the two fluxes with the harmonic potential as a regulator to have a discrete spectrum. And presented here is a plot of the ground state as a function of these two parameters. Again, note that alpha equals 1 is the same as alpha equals 0, when the flux is the multiple of the flux quantum. And the other three-body problem is two particles plus one flux. There's two standard anyons with statistics alpha in a harmonic potential with a flux gamma placed at the origin. Here, everything will depend on alpha and gamma. Again, we have studied the ground state, and it turns out that there are two competing states. The energy of one of them is known exactly. Of the other one, there is only an analytic conjecture because the energy has only been calculated numerically. So there is a somewhat non-trivial structure of the ground state here, and there is a level crossing where the energies of these two states meet. Well, I have played on the flag, but I have definitely stopped short of forfeiting the game. Thank you very much.
Exactly solve the problem of two interacting particles on a ring in an Aharonov-Bohm setting without the magnetic field actually touching the particle. So without having any Landau level picture. One can solve this problem, determine exactly the wave functions and energies and all that. And one could actually, my question is, could one use this idea, which I was not familiar with, of double interchanges to actually study these extra statistical factors that come out by using the exact solutions of such a problem, and then generalize to many more, not just two, but many interacting particles on an Aharonov-Bohm ring.
The rule of thumb is whatever can be done for single species anyons can be done for multi-species anyons in general. And two-body problems are simple anyway, so my educated guess would be yes, you could do that.